This section is on meta-analysis of continuous dataset. Continuous dataset like systolic blood pressure, pain score, weight, and height. And by the end of this section, you'll be able to conduct fixed and random effect meta-analysis, then be able to explore heterogeneity and conduct publication bias assessment, and use the following 5 steps to do this meta-analysis. Meta-analysis of continuous dataset, you need 6 different variables. You need the number in the intervention group, mean, and the standard deviation. That's 3 variables for each treatment group. The number, the mean, and the standard deviation for both treatment groups, making 6 variables. So we are going to use this particular dataset. I have all these fixed variable and the year of publication. I'm not going to go through how to enter dataset here one by one, but we are going to use a direct method where you just load the dataset from the Stata. So after loading the continuous dataset, then you can describe it. This is from meta-analysis by Rob Harris 2006. They reported the study ID, the year, and the all 6 variables that we need for the meta-analysis. So the second step is to declare, and let's start to know that I want to do meta-analysis of a continuous variable, and you have like 5 different options. So I've mentioned before, if it's measured using different scale, then you need to do standardized mean difference. So there are 4 subtypes, but the default one is Edge's method of calculating standardized mean difference. But if something like weight, height, systolic blood pressure, diastolic blood pressure that can be measured in the same scale, then go for unstandardized mean difference. That's MDiff. So for this analysis, we assume that this outcome, we are measured differently. So we are going to go for the default, the edges, and let's start to know that these are our 6 variable, and we've declared it, and we have total of 20 study. Then we start the meta-analysis by doing both the fixed effect and random effect meta-analysis. So this is the random effect meta-analysis, and as you can see, this is the pole effect estimate. So if along the way you find that this analysis continuous variable is measured the same way, you can update your method and just let's start another. Now I want to change it to the mean difference. So I want to use unstandardized mean difference. So I'm sure the variable will be measured in the same way throughout my study. Then you can start redoing the meta-analysis and generate the forest plot. Then you can explore heterogeneity. For this one, we just have the study year that we can check whether there's correlation between, and as you can see, it's not significant. There's no relation between the pole effect estimate and the study year. Then checking for publication bias, looking at the forest plot. This is symmetrical. There's no evidence of publication bias from the funnel plot, and if we do the formal statistical test, it shows there's no evidence of publication bias. So let's try and do trim and fail. As you can see, no study was inputted, so we can conclude there's no evidence of publication bias. So let's go to Stata and do this analysis. So the first step is to load the data set. So we have our data set in data folder. This clear just means that I want to clear any existing data that we have there. So these are our data set. So if you describe it, we have 20 observations. It's from this particular meta-analysis. So I want to declare that it's a continuous variable. These are my 6 variable. Then we have the edges standardized mean difference. Then I can generate my forest plot using meta-forest command, and I want to show the null effect here. It should be 0. Okay, so this is the meta-analysis using the standardized mean difference. It shows the intervention is not significant. It crosses the line of null effect, which is 0. Then we can update our method to mean different unstandardized one, just meta update, then effect size this. Then let's regenerate the forest plot. Still not significant. Then let's export using meta-regression analysis. So there's no association. So let's tabulate the year. This study was published between 1984 and 2005. So we can do sort of subgroup analysis. Let's look at the pool effect estimate for the older study compared to the recent study. So we can use recode again. So we want to recode year. So from 1984 to 1999, let's call it 1. So call it the earlier studies. Then any study published after 2000 to 2005, let's call this one 2. Then we label it as recent studies. Then we can generate new variable. Let's call it year category, year cat. So let's tabulate it and see what is the distribution of this year cat. So we have earlier study 12, recent study 8. So we can generate the forest plot for this one. So let's generate the forest plot. So there's no difference between the earlier and the recent studies. So we can conclude there's no effect of year of publication on the pool effect estimate. Then let's check for publication bias. So we look at the funny plot. The funny plot is symmetrical. There's no evidence of funny plot asymmetry. Let's test for it statistically using Eggers test. It's not significant. And let's see whether trim and fail still tell us the same thing or show that there's no study to impute. There's no evidence of publication bias. So we are sure that all the possible studies have been published. So this brings us to the end of meta-analysis of continuous data set, and we've briefly touched on the 5 steps in conducting meta-analysis and exploring heterogeneity and publication bias. So the last one is on the prevalent estimate. So you can go ahead and play the video or tutorial on that one. Thank you.